Good morning, class. So today we are going to talk about Newton's laws applied to, let's call it a two-body system. So we'll have a system with more than one object, and but there's some sort of coupling between the two objects. And in the case of today, that coupling is going to be transmitted via a rope or string, and that means tension. So we're going to take a look at that, and this connects with one of the homework problems. There's a problem that involves two masses that are connected via a pulley, and one's on an incline and the other's hanging vertically. So this work we do today should help you a great deal working through that problem. And then we'll move on and we'll take a look at a problem that involves a roller coaster going in a loop, and we'll think about what's happening at the top of the loop or near the top of the loop. And again, this connects with one of your homework problems that's assigned. Okay, so I hope you guys had a good weekend, and I I enjoyed looking at your results of your first computational lab assignment that was collected for a grade, the projectile motion one. You guys did a really good job on that. So there'll be more of that in a couple weeks. And all right, so let's get going. Oh, I posted a video tutorial this weekend on geez, I just made it. It is on the topic of, oh right, a car going around a curve, and then extending, what's it like if the car is on a flat surface versus there's banking in the curve, kind of like a NASCAR track. How does that influence the ability of the car to go faster around the curve? So those problems are framed in a way, that work is framed in a way where I'm asking, what's the maximum speed that a car can have and successfully go around a turn without crashing, without losing static friction and skidding out of control? And deriving some expressions from the physics that allow us to understand the connections between the parameters of the situation, such as how fast the car is going, what's the banking angle, what's the coefficient of static friction, what's the radius of the curve, and how all those things fit together. All right, so take a look at that tutorial. It's posted on YouTube. It's also linked to in this week's lesson on Sakai. All right, so, geez, look a little disheveled this morning. So let's do this, all right? Let's go over to the whiteboard, and you got any questions? Good morning, everybody. And if you got any questions while we're doing this, put them in the comments, and I'll see them. All right. Okay. Got my trusty tablet, my trusty Surface Pro. And so let me frame the situation for you here, and I'll draw a little picture. After a sip of coffee. All right. So the situation is, I call this a two-body problem, or two-bodied problem. I'll call it two-body problem. And the situation is like this. So we have a mass called M1, and it's sitting on a counter, a flat counter. And over here on the edge of the tabletop, there's a pulley, and then there's a string that goes over the pulley and then hangs down off the table. And there's another mass hanging down here. Call that M2. Okay, and so one thing is we're going to say that this pulley right here, pulley, is frictionless. And the reason we say that is so that we can assume, we'll use red to represent forces, that this hanging weight is going to exert a force a tension force, we'll call that T, on mass 1. And that tension is transmitted via the string, the rope. And that tension is the same magnitude as the tension that's pulling up on mass 2. So how do I know that? Okay, the frictionless pulley, the part about it being frictionless means that there's no force exerted by the bearings of the pulley itself on this system. All right, and so that force is transmitted perfectly from one object to the other. So how do I know those two forces are the same? Does anybody know? You can put it in the comments if you know. And while you're doing that, thinking about that, let's keep labeling other forces in a situation. So both of these masses will have a weight equal to m, their mass times g. Then this mass up here is going to have a normal force because it's resting on the tabletop. And there's also a frictional force which points in the opposite direction the rope is tugging. All right. And does anybody have an idea? What it's not just gravity for each, since they're part of the same system. It's not just gravity for each since they're part of the same system. William was asking about I guess I'm not sure 100% what William is asking, but okay, so we can, in a problem such as this, you can approach it sometimes such that you think of the whole thing, M1 plus M2, you think of the whole thing as one system. All right, M1, so that the total mass is M1 and M2. In this case, we're not going to do that because that would complicate things, and the reason is because one is getting pulled horizontally and the other is vertically. All right, so you got motion in two different directions if it's moving. Okay, it doesn't necessarily have to be moving if the forces aren't sufficiently large. The approach that I want to take is I'm going to think of each of these masses as individual objects, and I can draw a free body diagram for each of them. And when I say they're coupled, it means that one of the forces on free body diagram for mass 1 is equal to one of the forces in magnitude, that is, to one of the forces in free body diagram for mass 2. And so Nicole says they're on the same string, and that's how I know that the tension is the same. And that's true, and let's elaborate a little bit more. The tension forces here are a mass reaction force pair according to Newton's third law, that mass 2 pulls on mass 1 with tension T, therefore mass 1 pulls back on mass 2 with tension T. They're equal in magnitude, opposite in direction. They're an action-reaction force pair, and that's what couples this. Remember I said that Newton's third law is about interactions between objects? And so here we have two bodies, two individual objects, but they interact with one another via this tension force. All right. So let's do this. Like make this a little smaller, and so I'll do a free body diagram for mass 1. And so here's mass 1, and we got the normal force, we got the tension force, we got the weight, M1 times G, and we got, ooh, sometimes I click the eraser by accident, and then we got the friction force. Alright, and so for this free body diagram, I'll call up positive, there's two dimensions here, so I'll call up positive y, and to the right positive x. Alright, make this a little smaller. I'm trying to fit a lot here on this slide. Dude. Okay. And then for mass 2, we have, here he is, here's mass 2. We got the tension force directed upward, and the weight of mass 2 equal to m2 times g directed downward. And so for this one, I'm going to call down positive y. We don't even have to define positive x. There is no x dimension to this part. It's a one-dimensional situation. All right, and so for I tuck away in the back of my mind that the tensions, the T's in these two free body diagrams have the same magnitude. Now you can see they have different directions, but they have the same magnitude. All right, and we'll use that in a little bit. But now let's use Newton's second law to write down expressions for the net force on mass 1. And so mass 1 has two dimensions to it, so we'll have to write down two equations. The net force in the y direction here would be equal to the normal force, which points up, minus the weight, which points down. And Newton's second law says that's equal to mass times acceleration in that dimension, which is, there's no way that the mass is going to accelerate up and down, mass 1. It can slide horizontally, but it's not going to go up and down. All right. So from Newton's second law, what we have then is that the normal force on mass 1 must equal its weight. That's what this means. The normal force is equal to its weight. All right. What about the x direction? The net force in the x direction? Well, it's going to be the tension which pulls it right minus the friction force. And so let's pause here for a second. And what we write down here depends on, remember there's two kinds of friction, static versus sliding. So what we write down next depends on what's happening. Is this a static system or is this a sliding system? Is it accelerating or is it at rest? So let's do the at rest situation first. All right. So let's do that's supposed to be an at symbol, rest. And that means the acceleration in the horizontal direction is also 0. And that also means that the frictional force, well, messy. That means that the frictional force is less than or equal the coefficient of static friction times the normal force. So if it's at rest, it's static friction. And static friction is always less than or equal μs times the normal force. And then let's say, well, what is the situation where the static friction is as large as it can possibly be? Well, that's the situation where the mass that's hanging from the pulley is as large as it can possibly be before everything starts sliding. So let's pursue that a little bit. Let's ask, what's the excuse me, what's the maximum mass that M2, the hanging mass, can have before the system starts sliding? So we'll set up the problem using the maximum value of static friction in this expression, and then we'll figure out what M2 will be when that maximum static friction is attained. And then if M2 is any more, you drop a feather on top of M2, everything starts sliding. All right, so we will say here then that the tension force in that situation is equal to its maximum value. Or sorry, the frictional force is equal to its max. So in the x direction, you have a positive t minus the friction force, which is its maximum amount, μs times the normal force, and that's equal to the mass times its acceleration in the x direction, and we're pursuing the case where everything is still at rest, but barely. So we have tension is equal to the maximum amount of static friction before things start sliding. All right, so let's come over here and now change frames. So now we're looking at mass 2. And here we have, the net force in the x direction, 0. There's no forces in that direction. The net force in the y direction, I call down positive, so there's this weight, m2 times g pulling down, minus the tension, which pulling up, and that equals mass 2 times acceleration in the y direction. And again, we're pursuing the situation where everything is at rest. There's no acceleration. So the net force is 0. Excuse me. All right, so that means the force of tension is equal to the weight. All right? And so now, let's connect the dots. So one thing we can do is we can put the normal force in down here. So we get the force of tension equals mu sub s m1 times g, and then we have tension equals m2g. Set those two things equal to one another, and you have mu s m1g equals m2g, and we get this situation where there's a g on both sides, so the acceleration due to gravity doesn't matter, and we end with, I'll write it out one more time. What is the maximum mass that m2 can have before things start sliding? It depends on two things. It depends on the coefficient of static friction, mu s, and the mass of m1. So if you have more friction, this thing is sitting on rubber pad versus, a piece of glass, you're probably going to have more friction. So that would mean you can hang more mass before things start sliding. And the other thing is, if M1 is more massive, it can support more hanging mass before it starts to slide. Okay. All right. So let's then look at the situation. How do the equations change if the system is accelerating? And well, here let's use actual numbers for this case. Move this up a little bit. Okay, so let's say like this defines right here the maximum amount of mass that you can hang and everything stays still. So it's easy to set up a situation where you would exceed that maximum. So it could be like, let's say that you have a coefficient of static friction of 0.5. Make it a little bigger. 0.7, and M1 is equal to 4 kilograms. Well, if M2, the maximum amount that M2 could be would then be 4 times 0.7, whatever that turns out to be. So if M2, and which is less than 4, so if M2 is greater than that, so let's say 8 kilograms, this would set up a situation where things start sliding because M2 is greater than mu s times M1. So this would lead to sliding, and when that happens, the coefficient of static friction becomes the coefficient of kinetic friction, and that is always less than the coefficient of static friction. So let's say in this case it's 0.5. Alright, well, how do these equations of motion change? The main way they're going to change is the acceleration is no longer 0 for mass 1 horizontally and mass 2 vertically. Those accelerations won't be the same, they won't be 0, but they will be the same magnitude because the two masses are connected via the rope. So if this one's accelerating at 1 meter per second horizontally, the other one's accelerating 1 meter per second vertically because they're connected by the rope. So if we back up a few steps and find the place in our process where we eliminated the accelerations, and then we say, well, they're not 0, and then we write out these expressions and see how they combine. So let's say that we want to figure out what that acceleration is. Okay, so given these parameters, mass 1 is 4 kilograms, mass 2 is 8 kilograms, mu sub kinetic, mu sub k is 0.5. Let's find the rate of acceleration. Okay, so we back up a little bit to right here and right here, and we don't eliminate those accelerations because they're no longer zero. So we have for mass 1, we have, just write out that expression again here. So for mass 1, when it's sliding, we have T minus, now it's not mu s, it's mu k times the normal force equals m1 times its rate of acceleration, and that's no longer zero. So that's this rewritten. And for mass 2, we have m2 times g minus the force of tension equals mass 2 times its rate of acceleration. And here I just have 1a because they're the same in both, for mass 1 and mass 2 have the same rate of acceleration, magnitude-wise, different directions, but magnitude-wise. And then I can say, I know that the normal force is the weight of mass 1, so I can write that in there instead of Fn. All right, so I have these two equations, and you know, what are the similarities here? T, let's solve both for T, and then set them equal to one another. So the tension couples the two masses. The tension on mass 1 is equal to its mass times its rate of acceleration plus the magnitude of the tension force. And so this should make sense. What's the tension? Well, it's whatever the net force is plus whatever is needed to overcome the force of tension. And for mass 2, I gotta rearrange things here a little bit, and I'll move the minus sign around, so T is without a minus sign. So for mass 2, what is the tension? Well, it's less than the weight because it's accelerating downward. So it's whatever the weight is minus the net force, m2 times a. And then we can set them equal to one another. m1a plus mu k m1g equals the weight of mass 2 minus that. Let's group the a's on the left-hand side. So we get m1 plus m2, factor out the a, equals m2g minus mu k m1g, and divide both sides by the total mass. And we get the equation for the acceleration of this system. Zoom out here a little bit. Okay, so let me plug in the numbers. I'll actually get a real number here. So, why did I start writing? Okay, that's a little confusing. That is a mass, not a mu. My mu's and my masses look the same. All right, so m2, 8 times g, 9.8, minus 0.5 times mass 1, which is 4 kilograms, times 9.8, divided by the total mass, which is 12 kilograms, and I get A equals 4.9 meters per second squared. Okay. I just wanted to get an actual number there. So how is this different than your homework problem? When you look at your homework problem, what you're going to see is mass 1 is not on a flat surface, it's on an incline. So what does that do? Ah, I like building up layers of complexity, one piece at a time. So your homework problem looks like this. There's an incline. There's some angle of incline, and then you have one mass that's being pulled up the incline and one mass that's hanging off the incline, and there is a pulley connecting them. Okay, so how is this different? Oops, I hit that eraser button again. How is this different? Well, now the normal force is at an angle, tension force is at an angle, the force of friction is at an angle, or maybe you just say all those things, I rotate my axes, and all those things are fine along a horizontal or vertical, an x-axis or a y-axis. So what I'm saying is, for this mass, use axes that look like this. And then the difference here is the weight. If you use those axes, the weight of the mass on the incline has an x component and a y component. And so you would have to resolve the weight into an x and y component, and then your net force in the x direction will have one of those components. Your net force in the y direction expression will have the other one. For the hanging mass, the equations look the same. All right, so I think I'll leave it right there and see how far you guys get on this. But it's, so I'll say that one more time. The thing that's different about this problem compared to what we just did in detail is the weight of this block, mass 1, is going to have a y component, and it's going to have an x component. Okay, and you can resolve that using sines and cosines, just like the incline problems that we've done so far. So one of these terms pops into the net force equation for your net force in the x direction, and the other one pops into the equation for the net force in the y direction. And then proceed algebraically to find your solution. But the goal in that problem is to find the rate of acceleration, just like we did with the flat surface. All right, so let's change gears a little bit, all right? And the next thing I want to do is let's talk about roller coasters a little bit more. So the situation is you have a roller coaster with a loop, and where I grew up in central Pennsylvania, at Hershey Park, they had a roller coaster. I guess they still have it, called the Super Duper Looper. And the problem that we'll look at involves thinking about the forces that act on somebody when they're at the top of the loop. All right, and we will make the assumption that this is uniform, or this is circular motion. Maybe not, it's not necessarily uniform circular motion, but there'll be a centripetal, a center pointing force, and a centripetal acceleration. All right. Well, wrong one. Okay, here we go. So we'll call this, here, I'll show you the picture. Maybe if I show you the picture, just give me a second here. Web assign. Let me log in here. So here's the problem. Is the extension of what we were talking about with the two masses, but now one's on an incline, and you know the angle of incline. So the weight of this guy has a component that's along the incline and perpendicular to the incline. But the problem I'm talking about now is this one. 40-kilogram child is on a roller coaster, and see if I can get this all on the screen at one time. Here we go. A child of mass 40 kilograms is on a roller coaster car that travels in a loop of radius 8.5 meters. At point A, the speed of the car is 14.8 meters per second, and at point B, the speed is 15.5 meters per second. So already we know this is not uniform circular motion because the car is accelerating. It's speeding up. It's going faster. So it's accelerating tangentially to the path that it's following, but it's also accelerating toward the center of the circle. It has to. There has to be a centripetal force, in order to make the child go in a circle along a circular path. Assume the child is not holding on and does not wear a seatbelt, because that's a good assumption. So, all right, roller coaster. What we want to find, though, is what is the force down here? What is the force of the car seat on the child at point A, and what is it at point B? All right, so point A is right at the top, and point B is a little bit 30 degrees away from the top. Okay. So, all right, here we go. So roller coaster. And we're approximating this roller coaster loop as a circle. So I'll just draw a circle. And we have these two spots. Spot A is when the roller coaster is at the top. And here's the child sitting in the roller coaster car. And so that's spot A. And spot B is a little bit further along, where the child is 30 degrees. Spot B is 30 degrees counterclockwise from spot A around the circle. Okay. And so we're going to do, spot A first. All right, so at spot A, what are the forces that act on this child? Well, there is the force of gravity is always pulling down, equal to the weight of the child. All right, m times g. See, I'm not writing Fg or W anymore. I'm just writing out that weight is mass times g. All right, it's just, and what other forces act on the child? Well, the seat. The child is sitting in here in this car, and the seat is pushing up on the child's body. So that's a normal force. So in addition to the weight, there's a normal force that's pushing in this direction. And so the net force, here I'll draw a free body diagram over here a bit more carefully. So we have the child's weight, and then it's a little hard to draw two vectors that point in the same direction. We have the child's weight and the normal force, the force of the seat on the child. Okay, and we'll call, I wanted black, we'll call down positive. And so this is a case of circular motion. So that means the force that points toward the center of the circle is a centripetal force. And so the net force, I'll say net force sub C for centripetal, the center pointing force, the total force that's pointing toward the center of the circle that the child is traveling along, is equal to the sum of these two forces. They both point toward the center of the track. So the normal force, the force of the child's seat pushing up on the child, or in this case down, because she's upside down, and the weight of the child equals, so that's the net force, equals the mass of the child times its rate of centripetal acceleration. And centripetal acceleration is v squared over r. So we have the net force, the net centripetal force, which is the sum of normal force plus weight, equals the mass of the child times her speed squared divided by the radius of curvature. And so in this problem it says, what is the force pushing up on the child, the force of the seat? What's how they word this? Hold on, read it. What is the force in newtons of the car seat on the child at point A? Enter magnitude. So what is the force of the child's seat on the child? What's that asking for? It's, oh, I hit that erase button again. It's asking for the normal force. So we solve for it. The normal force is then equal to mv squared over r minus mg. And so in this problem we know all these things. The mass of the child is 40 kilograms. The speed at point A is 14.8 meters per second. The radius of the roller coaster loop is 8.5 meters. And g is 9.8 meters per second squared. And so let me plug all those things in here and I'll give you an answer. 639 newtons of force. So let's go back to here and let's put it in, make sure we're right. 639 newtons, submit. Good. Okay, so the interesting thing here is, what is the child's weight? The child's weight is the child's mass, 40 kilograms, times g, 9.8. The child's weight is 392 newtons. 392 newtons. So at this speed, the seat is actually pushing down on the child harder with more force than the child's weight. And so the experience that the child will have then is, remember, the sensation of your weight is actually a consequence of the normal force of the thing you're standing on or sitting on pushing back on you. Remember the elevator? Why do you feel lighter? Why do you feel heavier? You're not actually lighter or heavier if you're accelerating downward or upward in the elevator. So here, the fact that the normal force is greater than the child's weight would mean that at the top of that loop, the child feels heavier than she actually is. She would feel like she's being pushed down into her seat by this crushing weight of gravity that's like 2 times her normal weight. Who the heck is Dana Rodriguez? How do I block people? Remove. Put user in timeout. I put her in timeout. Unbelievable. Anyway, you feel heavier than you actually are. All right. So what about the next part of this problem here? Well, for the next part, they want to know, what about at point B? Well, at point B, the free body diagram looks different. At point B, let's rotate our axes here so that the direction toward the center is still, so we'll rotate our axes so that the direction toward the center is, I don't know, called positive y, whatever, and then the direction that's perpendicular to the circle, positive x. And So the forces acting on the child at point B would be, you'd still have the seat pressing the child toward the center, and you'd still have the child's weight pulling down. Okay. And so now, what's this angle right here? It's 30 degrees. Let me zoom in here a little bit. So when you're solving part B of this problem, what you're going to do is you're going to recognize that now only part of the weight of the child is center pointing. What part? Well, it'll be equal to mg cosine theta. That's the part of the child's weight that's center pointing. The other part is not center pointing. So when you write down an expression for the net centripetal force, the center pointing force, that's the force that's going to be along what I called the y-axis here, you're going to have the normal force plus that component of her weight that's pointing along that axis, and that equals her mass times her rate of centripetal acceleration. So the only difference here is now instead of saying Fn plus mg, it's Fn plus mg cosine theta equals mv squared over r. So you still have a centripetal acceleration, and now in the problem the v is different. You've accelerated a little bit, you sped up a little bit because you're coming down the hill, but you solve for Fn, just like you did in part A. Alright, then there's a part C to that problem. And what is the minimum speed required to keep the child in his seat at point A? Alright, so part C says, let's go back here, forget part B. What's the minimum speed? Min V, so child stays in the seat. And you got to do a little bit of interpretation here. What does that mean? As the roller coaster slows down, the amount of centripetal force will become less and less. The amount of centripetal force required will become less and less. And until the seat is no longer necessary to help supply that centripetal force. The normal force isn't necessary anymore. In other words, the child's weight is sufficient to supply the centripetal force, the center pointing force. So in this problem, part C, what's it saying? Find V so the child stays in the seat. That's another way of saying is find V so the normal force is equal to 0. And so we just back up here to our equation of motion up here. Circle it in blue. Circle it in red. Right here. And we just bring it down here, and we solve for V where Fn is 0. So Fn is 0. And then using the parameters given, solve for V. And so you'll get something, I don't know, I got like 9.13 meters per second. Okay. So if you're going slower than that, you'll fall out of your seat. And if you're not wearing a seatbelt, that's bad. So I gotta assume that most roller coasters are designed that if you're going upside down, the motion is sufficient that the centripetal force requires some component of the normal force, the seat pushing up on you, or if you're upside down, down on you, and as a margin of safety. In other words, I would think most roller coasters are going to be designed so that the restraints are, if there's a catastrophic failure of the restraints, that a person is still not going to fall out. of the roller coaster. So the restraints are there as a backup. All right. R.I.P. Dana left a dislike. Oh, nice. um, so that's the first time we had somebody who is should we call him a troll join our live stream and start making unpleasant comments. Actually, nonsensical comments. All right. So all right, that's enough for today. Anybody have any questions before we call it a day? Looking at your comments. Anybody? All right. Well, then I will see you guys tomorrow for the lab session at 1:50. And this week's lab involves Hooke's law. All right. So Hooke's law is another force law that deals with springy things, elastic things, and it's you'll be using Excel and you'll be using Tracker, and but in a little bit different way. All right. Don't see any comments, so I will see you tomorrow. Have a good rest of your day. Bye-bye.